In this lecture, we are going to discuss the concepts of covariance and correlation. I always like to start my discussion of correlation by looking at the word correlation. As you may already know, correlation describes how related two random variables are. For example, weight is correlated with height. The taller you are, the heavier you are, generally speaking. Another example is that your exam grade is correlated with how much you studied. Generally speaking, the more you study, the better your grade. Many people don't notice this, but the definition of the word is in the word itself. Correlation is just the combination of two tokens, co and relation. In other words, what is the relation between two co-occurring features? To explain what the point of this is, let's remember that currently, our job is learning how to describe and characterize our data. Correlation helps us do that. For example, we might notice that every time the S&P 500 goes up, so does the Dow Jones Industrial Average. This is called a positive correlation. We might also notice every time that gold goes up, the dollar goes down. This is called a negative correlation. At this point, this is pretty much all we can say, but we can do a little bit of foreshadowing. Correlation and covariance will become very important in later sections of the course. It's going to pop up again when we talk about time series analysis, and again when we talk about portfolio optimization. So suffice it to say, it's an extremely relevant concept in finance, although at this point, it may just seem like a mathematical curiosity. I found that this picture is a pretty good description of correlation. When the correlation is 1, that means there is perfect correlation between two stocks. That means whenever one stock moves up by $1, the other stock moves up by, say, exactly $3. Whenever the stock moves down by $1, the other stock always moves down by exactly $3. That describes a perfect linear relationship between the two stocks. Note that the correlation is always between -1 and +1. So -1 describes the opposite situation. When one stock goes up, the other goes down by some constant amount. Anything in between describes a more noisy relationship. That is, when one stock goes up by $1, the other stock goes up by $2, but on another day, maybe the other stock goes down by $0.5. In other words, because the linear relationship is imperfect, the other stock is harder to predict accurately. And that's what happens when we have a correlation less than 1. Zero correlation means there is absolutely no linear relationship between the stocks. In fact, we will make plots exactly like these between pairs of stocks in order to check how correlated they are. Okay, so now that intuition time is over, what does correlation really mean? Well, correlation depends on covariance, so we have to discuss that first. As you may be able to tell by its name, covariance is closely related to variance. As you recall, variance is defined as the expected value of a random variable minus its mean, all squared. By the way, if it's not clear by now, whenever we talk about these statistics, we are usually talking about the return and not the price. So everything in this lecture is in relation to stock returns and not stock prices. Alright, but now, let's suppose we are managing our own hedge fund, and we have a set of 500 stocks. Now we can ask, what's the covariance between stock return I and stock return J? That's defined as the expected value of Ri minus mu I times Rj minus mu J. Here Ri is the return on stock I, and mu I is the expected value of the return on stock I. It should be clear that the covariance between a stock I and itself is just a regular variance. From here, we can define the covariance matrix. The covariance matrix is just a matrix that collects all of the possible covariance and variances into a square. The element at row I and column J is the covariance between stock return I and stock return J. Furthermore, the elements on the diagonals are the variances for each stock return. Note that if we have D stocks to consider in total, then this matrix is of shape D by D. Also, because the definition of covariance is symmetric in I and J, the covariance matrix is a symmetric matrix. That is, the element at location ij is the same as the element at location ji. Now, somewhat confusingly, we usually write all the diagonal elements as sigma I squared. That makes sense because this is just the variance. However, for the off-diagonal elements, we write them as sigma ij without any square. This is despite the fact that the units of sigma ij are still squared units. So just keep that in mind. Now, although we will never have to do this calculation in code, it does help to see how one might calculate the sample covariance from a dataset consisting of multiple stocks. Let's suppose I have an n by d matrix of stock returns. That is, I have n samples and d stocks, as we typically represent data in statistics and machine learning. I want to calculate the d by d covariance matrix for these stock returns. First, I calculate the sample mean of each stock return. This gives me back a vector of length d. We'll call that r bar. Then I take the big R matrix, subtract r bar, and multiply that by itself. Then I divide the result by n-1, which gives me the unbiased estimate of the covariance matrix. Note that I'm assuming that broadcasting is being done so that we can subtract a vector from a matrix. Mathematically, this is incorrect, but it would work in code, and this makes it simpler to write down. Note that we can also write this in outer product form, which does not require any broadcasting. This is because R sub n is a d-length vector. It's just the nth row of the matrix R. Alternatively, you can just calculate each element one at a time by doing the sum over all little n from 1 up to n of Rni minus R bar I times Rnj minus R bar j, and then you take that sum and divide by n-1. As an exercise, you might want to test this calculation against the cofunction in NumPy. Okay, so I promised that the correlation is somehow related to the covariance. In fact, the correlation is just the covariance, scaled by the standard deviations of I and j. In other words, the correlation between stock I and stock j is the covariance between stock I and stock j, divided by the standard deviation of stock I, divided by the standard deviation of stock j. This also explains why the correlation is always between -1 and +1. This is a natural result of scaling by the standard deviations. Because of this, note that we can also define the correlation matrix, which is just a matrix that collects all of the individual correlations in a table. Also, since the covariance between stock I and itself is just sigma I squared, the variance, if we divide that by sigma I twice, we will always get 1. Therefore, the correlation between a stock return and itself is always 1. That makes sense. There is a perfect correlation between a stock return and itself.